my talk is based on just recent paper. It is preprint in arXiv, joint work with my colleague from Italy, from the University of Udine, Roberta Musina. I take the space RD, Z is the variable in RD, and it is split into two parts, Y in RK and X in RD minus K. And I wish to consider this inequality, and it is in fact a generalized Hardy inequality. If you put A and B equals 0 and gamma equals 0, it is standard Hardy. Yeah. In some other cases also were investigated earlier. Yeah. P is greater than 1, and A, B, gamma are some parameters, but to discuss this inequality, first of all, I should require that the quantities in the left and the right hand side exist. For example, for C infinity compactly supported functions U. This means that the weighted in the left and right hand sides should be locally summable. And it means, yeah, here are two places where it is a question, the summability, local summability is a question. If y is 0 and z is 0 and infinity, surely. And this means that k plus a should be greater than 0. It gives us summability here. This inequality gives us summability at the origin, and this inequality gives us summability here, where y is 0. If this inequality holds with some positive constant for all smooth and compactly supported functions, then we can take this space C0 infinity and complete it with respect to the norm in the right hand side. And we obtain a weighted homogeneous Sobolev type space, which is called D1P with corresponding weight. What we know, what we knew before our work. First of all, the so-called purely cylindrical case. Under this assumption, we can drop B and gamma and obtain the inequality with this weight, and it turns out, it is almost obvious, that the sharp constant in RD coincides with sharp constant in RK. You see here S 0, 0, B and gamma is 0. And it is written here, and I will call it lambda 0 in power p. And it is well known that this constant is not achieved. The next case, quasi-spherical case. It was investigated in our previous paper jointly with Gabriele Cora. It was published in this year. Why is it quasi-spherical? If we put a equals 0, then we obtain purely spherical weights. And it turns out that the behavior is quite similar to the purely spherical case. In this case, the weight gamma is just p plus b, and the constant is this one. And you see that if b equals 0, it coincides with classic, excuse me, if a equals 0, it coincides with standard Hardy constant in RD. Well, and this infimum is also not achieved on the energy space. In this paper, also similar inequalities in cones were investigated. Now we consider a general case, so all possible admissible values of parameters A, B, gamma. First of all, it turns out that the sharp constant, under the necessary conditions, one is just local summability of all weights. This constant is strictly positive if and only if gamma is greater or equal than B. Let me draw something. Here we the inequality we have no this inequality, or we have this inequality with constant 0, which is empty. Also, we consider a related inequality, related constant. S B gamma is sharp constant in the original inequality, and here we consider the corresponding quotient on the sphere. What is written here? It is a weighted norm, weighted Sobolev norm on the sphere, and it is a weighted Lebesgue norm on the sphere. So it is Hardy type weighted. This quotient corresponds to Hardy type weighted inequality at the sphere. What is the weight? Pi sigma is simply y divided by norm of x. So it is the operator pi is the orthogonal projection of z to y. Or you can say that absolute value of pi sigma is a cosine between y and z. Yeah, and this space is just weighted Sobolev type space on the sphere. And it turns out that under necessary conditions, these two constants coincide. Why is it interesting? Okay, we say that one unknown quantity is equal to another unknown quantity. In a sense, this quantity can be touched by hands. Not always, but sometimes. Also, we prove that for a given b, this function is continuous. It's evident but not trivial, and strictly increasing with respect to gamma. Yeah. So. The case gamma equal to b, we call it the bottom case. In particular, it includes purely cylindrical weights. It is more difficult for investigation. Okay, here I recall the necessary conditions. In this case, first of all, k plus a should be greater than p, and another condition for b, it is from minus infinity up to some quantity, which is in particular p times h0. I recall h0 is classical Hardy constant. H0 in power p is classical Hardy constant. Now we consider the bottom case. So you see SBB gamma equal to b. This function, so it's the function on this line. It is locally, and here is the right border. This function is locally Lipschitz continuous and non-increasing in B. In gamma, it is increasing, even strictly increasing, and on this line, it is non-increasing in B. Moreover, here is some point, B star, no, B star here. In general, it can be from 0 and strictly less than the right border of this interval, such that this sharp constant is equal to lambda 0 in power p, purely cylindrical case, here, and strictly less than this case, than this constant to the right. And moreover, here it is a constant, and to the right it is strictly decreasing. The next question is the question about attainability. As in classical Hardy inequality, this constant is not achieved in the energy space, is never achieved. What about S tilde? It turns out that up to this line, the S tilde is always achieved. This explains why I said that it can be touched. We can approximate it well, so because it is achieved. To the left of this line, excuse me, to the left of this point B star, on this border line, it is not achieved. To the right of this critical point, it is achieved. And what happens here in this point? We don't know in general. Except for the case p equals to 2. Yeah. Okay. Руки короткие. What about proofs? Okay, I will not explain the proofs. They are very very curved, I can say. We went from S to S tilde, then again to S, and several times. But two main tools are these two theorems. The first is a variant of theorem by Pinchover and Tinterev. Let's look to this equality with some constant m, positive constant m. It is the Euler-Lagrange equation for the minimizer, if this minimizer exists. It turns out that these three statements are equivalent. First, or the last, that the sharp constant is greater or equal than this m. The second, this equation has positive and lower semi-continuous weak supersolution, and this equation has a lower semi-continuous and positive solution. Locally, not necessarily in the energy space, but locally in the Sobolev space. And the second theorem is as follows: that if we put here just the sharp constant, then surely this holds. If m is equal to this s, so we have a positive solution. And let U capital be this positive solution. If it is not in the energy space, then this sharp constant is not achieved. So, так. Here it is written the definition of weak supersolution. This inequality should hold for arbitrary positive good test function. And if we have equality, then it is a weak solution, surely. Let me explain one of the parts. Other part is much more technical. Let us have a positive super solution. Then I wish to prove that the sharp constant is greater or equal than m. First of all, I write this inequality, it is just this one, using as test function such quotient. Then I open these brackets and use the Cauchy inequality. Here is the result. And then I use in these brackets the Young inequality. And magically I obtain just the right-hand side. And that's all. This is an old idea, maybe in some more simple case, and it is only a sketch because I should make some approximations and so on, but the idea is just this part. Так, how much? Сколько времени у меня? 8 minutes. Okay. Then I explain theorem B. Theorem B. In theorem B, this is sharp constant. This m is sharp constant, and we have U capital is a solution. And let us imagine that the sharp constant is achieved. Then I take U as a minimizer, and U capital is our positive solution. Here I have equality, because it is a solution. But I should have equality at the end. This means that this should be equality, and this should be equality. But when we have equality in Cauchy, when corresponding vectors are parallel, this means that gradient of U capital and gradient of U small are parallel. When we have equality in Young, it should be some equality between ingredients. Yeah? And this means that gradient U times U is equal to gradient of U capital times U capital. And gradients are parallel. This means that this equality holds without absolute values, but it means that U small is proportional to U capital. But U capital is not in the energy class, a contradiction. Okay, again, in fact, we should approximate and so on and so forth, but the algebra under this proof is just what I said. Okay, the next question is about this strange quantity B star. In the theorem, in the main theorem, I said that B star is non-negative. Oh, 5, okay. In fact, it is almost positive. It is positive if D minus K is not 1, always. But if D minus K is 1, it is positive if P is greater than 3/2. Yeah. It is very strange, and we conjecture that, in fact, it is always positive, but we cannot prove it. How to prove this fact? For b equal to 0, this we put alpha is equal to 0, and this function y in the power minus lambda 0 is just a positive solution of this equation. No, this is inequality, but it is even equality. It turns out that if b is positive and small enough, we can take positive and small enough alpha such that this function is a super solution. And then theorem A gives us this inequality. And what is this B star? It is the right border of the set where this sharp constant just equal is just equal to lambda 0 in power p. Yeah. And it is always less or equal than this. Okay, this proof again is to begin and to finish, nothing more. Also, we provide some estimate from above. Well, it is simple, but it is not sharp. I don't know. And finally, in the Hilbertian case, the picture is complete. We know all. First of all, we know what is B star. It is explicit. You see that it is not so simple. And we know that to the right of B star, the sharp constant is strictly less than lambda 0 here in power 2, p equal to 2. And here is this sharp constant. And we know that in this case, S tilde is achieved to the right of B star. And in fact, it is achieved by this function, cosine in some negative power. And here is this explicit power. And that's all. By direct calculation, it is interesting to mention that the explicit value of this SB gamma is known in the previous case, in the quasi-spherical case, gamma is equal to B plus P. No, B plus 2. And if gamma is equal to B, in other cases, we can say nothing about explicit value, but nevertheless, all what we can. Thank you for your attention.